So we're dSPACE. We do lots of things. We're a German company based in Paderborn. We've been around for over 30 years now. And we specialize mainly in the automotive industry, although we do have our talons in things like the aerospace and the industrial controls industry. And we build a variety of different things and at different areas of technology, from rapid control prototyping through to code generation, through to engineering management. But what I'm talking about today is hardware-in-the-loop simulation. And for those of you who don't know what a hardware-in-the-loop simulator is, it's essentially a computing device that's there to emulate the behavior of the plant, the thing that you're trying to control, for the purposes of testing the electronic control system. So testing the functionality of the electronic control system in a closed-loop way. And the way that it does that, it has a mathematical model that runs inside the hardware-in-the-loop simulator that represents the dynamic behavior of the thing that's under control. And it has a number of cards and a number of electronic devices which are there to, number one, mimic the behavior of the sensors so that we can understand what the state of the model that's running is and represent that in the same way that the sensors on the real plant would do. And number two, devices for capturing the actuation signals from the control system so that that can be fed back into the, to the plant model so that we can have a good understanding of what's going on. And what we do with hardware-in-the-loop simulation is we'll build these things, hardware-in-the-loop simulators. They look like that, or various other instances of them. And essentially, they're representing the behavior of the hardware. And traditionally, before electric devices were that common in the automotive industry, or electric power devices, rather, were more common in the automotive industry, we've provided hill simulators for what we call conventional internal combustion engines, for body electronics, for chassis controllers. You name it inside the vehicle, if it's controlled by an electronic control unit, dSPACE has built a hill simulator to be able to accommodate it. And what we found for most of those traditional types of systems is that we were doing what was called signal level simulation. What we were essentially doing is mechanical or even electrical signals or actuations were being converted at a signal level. And typically the kind of voltages that we were dealing with was around about the 5 volts. It was the milliamps level, because that's the way most sensors work. Most sensors operate on that type of low level. And a lot of the simulators that we built up to that date were what we would call signal level simulation. But we'll see that with larger systems, electric drives, batteries, motors, things like that, inverters, it's at a power level. That what we have to do is to manage the flow of energy as it goes through the system. And so here's a typical signal level simulation, certainly from the electrical side of things, is that we'll have our ECU, and our ECU is talking to the outside world through some kind of electronics, which is providing a stage between the real electric motor power as it's running through the system and the power stages. And what you're typically talking about here is an ECU that talks to the outside world directly through digital inputs, analog to digital converter devices, that sort of thing. And so when we are achieving, or when we're trying to perform hardware-in-the-loop, dealing with that type of signal level is not so much of a problem. It's a very flexible and scalable approach. We don't have to worry too much about the energy flow that's going through the system. We don't have to have any particular safety restrictions. There's no real particular challenge when it comes to providing electricity to the lab or electricity to the devices. And it's a convenient way of doing things. The alternative is to do it at power level. The alternative is to say, well, instead of having a hardware-in-the-loop simulator that represented at a signal level, I'm actually going to have a hill simulator that can deal with the real power, that can have variable loads, that can have power supplies, that can accept and output, sync and source, these large power systems. And this is the type of system that we've got here. And we call it a power level hill. Okay, so what are we talking about when we're talking about signal level simulation? Well, I've already spoken about that. We've got power electronics control, we've got current sensor feedback, we've got all those aspects of the system. And at that level, one of the things that we're going to need to do is to provide a model. Because I've spoken already about the idea of a hardware-in-the-loop simulator. being essentially a model that sits within the Hill simulator to represent the dynamic behavior of the system. And there's two types of ways that we can represent models within a Hill simulator. First of all, we want processor-based. And secondly, we can do it at FPGA level. Now, first of all, processor-based means we're dealing with a system whose dynamics is relatively slow. They're not high-frequency behavior. In other words, the models that we have don't need to run that fast to represent the behavior of the system and to generate the types of outputs that we need for the sensors. And so at that level there, we can often perform at the processor level. Processor we consider to be relatively slow. But when we come to electric drives and electric motors, when it comes to the commutation signals that you get off them, and when it comes to the dynamic behavior of them, quite often we found that processor level is not sufficient. We need to have an ability to be able to run the dynamic behavior much more quickly, and for that we turn ourselves to FPGAs, or field programmable gate arrays. And what we have is a set of libraries which contain the main components that you'll often find within a hardware-in-the-loop simulation for the plants that we want to be able to simulate. So for processor-based simulation, what we actually have are Simulink models, software-based representations of the dynamic behavior of the system that cover all sorts of main model components, such as permanent magnet circuit, BLDC, squirrel cage, three-phase inverter types of systems. But when it comes to FPGA-based simulation, what we also need to have is a corresponding set of models, but those models, rather than being processor-based, are IP core-based or FPGA-based. And so what we've done at dSPACE is build up this library of models, one for processor and one for FPGA. Now, broadly speaking, the processor models are much easier to deal with and much more flexible, but slower. And the FPGA models are much faster and give you much better performance, but there are big challenges when it comes to trying to implement those models and deal with the challenges of things like the behavior of floating point within FPGAs. And so they represent a challenge to us. And what we find with our drive models is that broadly there's a trade-off between the features and the capability and the fundamental frequency that we can run these typical types of systems at. Now, when we're coming to simulating on a power level, we still need models. When we're simulating the behavior at that power level, we still need models, but we're dealing with systems where we're talking about high current, high voltages going through the actual system itself. And so there are many special demands when it comes to those systems. We need to have proper cooling of all the power components. We need to make sure that the health and safety requirements are met. We need to deal with the behavior of full energy systems. And typically, the way that we'll do that, for example, in, say, a battery system, is we'll have our Simulink models, or we'll have our FPGA models. For batteries, the behavior is relatively slow, so we can normally turn to Simulink. And we use those models to control significant components that represent the behavior at the power level. So that's things such as power supplies, sometimes with the battery systems with loads. And when it comes to e-motors, we do the same. We have Simulink models or FPGA-based models, which are used to control the behavior of things such as variable loads, to get the variable loads to represent the characteristics of the e-motor, so that the power flows properly through the system. It represents the behavior that you would find in the real world. And then those signals are then fed back into the Simulink model to provide us with some closed-loop behavior as well. And so what we have is a number of different types of loads that give us the ability to be able to represent the dynamics at a power level. And so there's one of our special high-voltage customized loads that dSPACE provides that can build itself up to 75 amps. And these loads can be used in conjunction with one another, either stacked in series or in parallel to be able to achieve what you want. So, I promised I'll stay to time. This is the final slide, just to provide a summary. What are we really saying? Well, we're saying that when you're dealing with electric systems, one of the challenges of electric systems is that sometimes you can do it on the signal level, and sometimes you have to do it on the power level. Why do you have to do it on the power level? Well, there's a variety of different reasons why you have to do it at the power level. Sometimes it's because the provider of your ECU doesn't give you sufficient information and sufficient detail to be able to do it on the signal level. You've been given an ECU, and all you know is you've got to put 75 amps through that ECU to make it representative of what's behaving, of the behavior in the real world. And you don't have the connections or the circuit diagrams or the interface with the supplier to allow you to be able to do that. Or you might want to know really what does that ECU do when you put 75 amps through that particular system. So there is a choice there. Are you going to do it at signal level or power level? And the choice depends upon what access you've got, and it depends on the nature of the test, the types of things that you're trying to do. Now, essentially, signal level is low cost. It relies on high performance models, but it's a much lower option than the alternative, which is the higher cost. But sometimes you're going to get better results from the power level than you're going to get from the signal level. But it depends on a number of different factors. It can depend upon the models. It can depend upon the behavior of your ECU. It can depend upon what access you've got to your ECU. And that's just a short overview. So I just wanted to provide that as a short overview to some of the capabilities that companies have in terms of providing testing for electric hill systems, and also to give you an understanding that there is these two approaches, the signal level and the power level. And with that, I'd complete and say we have a stand out in the main hall, and if people want to come and talk to us in a bit more detail about the types of things that we can do and the challenges that we've got, then I'd be more than happy to do that. Okay?